Hello, thank you for tuning into this video focusing on nested structures for data analytics in the R environment. One of the emerging challenges in data analytics in this day and age is not in addition to the sheer volume of data and the velocity at which analysts receive it, it's also the variety of data, the diversity in how data could be expressed and serialized. And this both falls under structured and unstructured file types. Under the umbrella of structured data formats, likely data analysts will encounter three categories of data files. The most conducive for the analytics environments is the text delimited format. And this comes in the rectangular structure, two-dimensional rows by columns. The more we all are well aware of them: comma separated files, CSVs, tab, pipe delimited structures, and these map nicely, seamlessly into the two-dimensional structures or data frames, data sets in those particular softwares or environments. However, data can also be expressed in more nested structures, and which is actually the purpose of this video. Is a quick primer on how to what these two XML and JSON really are, and how analysts can really work through them. And these follow a different setup that requires the analyst to work with specialized tools to extract the needed data and map them into the nice data frame structure of rows by columns. And then comes the binary file types. These are extensions of software such as Excel spreadsheets, SAS data sets, Stata data sets, MATLAB files, and then R has its own type of binary types, RData and RDS, and these actually are tends to be faster to ingest into our environments simply because you bypass that parsing aspect of the text imports. And so to open, to demonstrate how to work with these nested data structures, I'll be using example data from City of Chicago, CTA's monthly L rides. And just as a quick introduction, what is the XML data type? Stands for the extensible markup language. It's really essentially a set of rules for encoded documents. And it follows the tree-like markup structure. You'll see or hear notions of root, follow with descendants, siblings across the elements, and attributes down the line. And I'll walk through and showcase this a little for you with the CTA data. This has been a decades-long industry standard format. It's been around in the advent, really the beginning of the computing age, but has really taken off and really has been standardized within the early days of the website, namely in the mid to late 1990s. And many domains really have adopted XML into their core protocols and practices. You got for spatial data, the KML is an XML type, MathML, Music XML. For those specific domains, RDF for documentation, RSS news syndication, SVG for graphics analysis, and these are all XML extensions formats. And then XML really is used for in APIs, which data analysts will probably be using for various original business documentation or feeds from various portals. Then there's archives, data dumps, and metadata. And so somewhere in the data analyst journey, they will encounter XML data formats, and hopefully it will not be a formidable endeavor. So again, we'll be using the City of Chicago CTA monthly L rise that actually exports data for in various formats, including CSV, but also XML. Two popular packages to use to navigate XML documents is the older package, all caps, XML, and then the newer lowercase XML2. And so these are two different packages that really do the same thing, navigates and extracts queries data through from XMLs into various end use needs for the data analyst. First step you always want to do is you want to parse the data so you can retain it into a tree like internal document for your parsing needs. Once we import that from its disk file, we see how the structure is. One thing to know about XML is that there is no standard format. Unlike the text delimited, which always comes in a rectangular row by column, XML does not follow a standard format. That's why it's one of a challenging type. But the more popular types tend to be these shallower types, and this is probably the best format to migrate into the two-dimensional data frame structures. As noted earlier, you have the root with an XML document, and every element opens and closes with its same name, and within it, retains its descendants. And so what we'll be needing is each row. Notice how they're serialized, they repeat nodes or elements, but the content themselves change with each row. And so we'll be mapping each of these row elements as rows into the data frame, and then each of these child of the row will become its own column. Now there's also an element known as attributes. These are encapsulated within a single element, denoted within by key values with the equal symbol. And so we'll also need to map these, sometime, for this particular document, this is more web metadata, but you may have in different XML files, attributes may be very pertinent data for your needs. And so how do we ingest this into a nice data frame format? The XML all caps package has a nice convenience handler for very shallower types, such as this. This is a very shallow one level nested file format. And then it's analogous method. This is an internal, it's an undocumented method denoted with the triple colon that maps essentially the attributes rather than just on the elements. So we need to bind both, navigate through all row elements, retrieve all its element values and retrieve all its attribute values, and then map it into a nice, tidy, two-dimensional structure data frame. And so again, this is not an end-all be-all method. This is only for shallower types. This will come in handy. XML2 does not have such a convenience method. You'll have to do a more nuanced way. And sometimes this could be good, right? Because now we can go under the hood and really, for more readable and maintainable code base, what you want to first do is retrieve all of the needed records or, for extraction. And this is essentially all of those row elements, and then map them accordingly. Retrieve all its attributes, underlying attributes, and all its children. Iterate across those records, map them into a nice data frame with their actual values and their corresponding names. Map them into a data frame. Each row becomes a data frame that we then stack together on the final call outside of the loop to get the same and final tidy data frame set. One great aspect of working with XML is because some documents can get very dense and nested. There's a tool known as Xpath. This is a query language to search and retrieve nodes within XML documents. One great aspect of Xpath is that we can even condition further on the needed subset of data. You see, XML wasn't designed or built for the data analyst in mind. It was built for other uses. But the data analyst comes ad hoc to use such data. So you may not need all of the data in the XML. So you may need to parse subsets across various nodes. For this particular example, we're gonna, we were actually using Xpath earlier, only a very simple, just extracting by the node name, but we can actually extend it out and within brackets, call various logic, both string, searches as well as mathematical expressions. So here we'll retrieve all of the CTA monthly L rise data for the Harlem Lake station stop, where average weekly rides is over 4,000. And so we essentially just did that. And so we get a smaller data set for that particular condition. And so XPath can really come in for navigating for specific extractions. And so, as I said earlier, XML does not come in a standard format. It really can be nested in various nuanced ways. And so this is actually an example of that. Notice earlier we had row and we had a flat set of child elements. This time the data all the station data resides as attributes within the station element. Month remains as is, and then all of the rides data is encapsulated within a rides element. And so now it becomes a little more nuanced. And again, it can get even more complex than this. But how to navigate through this will require more nuanced steps. With the XML package, you can now do a more, granular extraction with the Xpath sapply call, and walk through each of the needed elements and bind them into a data frame constructor call. Here we extract all of the attributes of the station. Then we extract month as is, its XML value, and then with the remaining rise data, we'll walk down into row rise level rather than the row level. So it's row station, row month, and then row rides will retrieve those specific element values and bind them all together into a nice data frame call. We could still call it our nice convenience handler, only it'll take additional steps. We now bind 3 elements together because there's 3 sets essentially: the station attributes data, and then the row data, the month data, and then the row rise setup, and then get that nice tidy data set. So again, these are all just tools that will be needed because XML is just a very different way of expressing data. And finally, XML has yet another great tool known as XSLT, a scripting language to transform whole documents. This is actually a sibling of Xpath. Xpath, recall, only queried within XML documents. XSLT is a more broader format in that it transformed XML files into the needed end-use needs for various reasons. And this is not limited to just R. This is an industry language that with the XSLT package in R, we can run. And so really what it is it's coding language. It's actually written in a valid XML format. Only it has special element values that really are sending commands to the XSLT processor. So what we're going to do is we're going to work from our nested framework and we're going to flatten it out to get it to our final end use needs. And so we walk down from the row, the response row, down to row, and then we're going to restyle. We're going to design the row elements, map the original attributes into new elements, station ID, station name, and then bind, copy over the month attributes, and then all of the children of rise. Notice the /* to get it into a nice flatter format. That we can then use our aforementioned methods to map into a nice data frame overall. So XML, while it's a challenging data type, it really has many tools for the data analysts to really work with it. And so get keen on XPath and XSLT, and you can really do various powerful things with any type of XML file. And then comes the JSON data type. This is stands for JavaScript Object Notation. And instead of the tree-like structure of XML files, it really follows a mapping key value framework. This is an emerging web application data format, really at the advent of a lot of the interactivity of websites, and you can really serialize and transfer data much easier than the XML to many programmers. This can be embedded within HTML documents. It can be pulled, extracted really easily from backend sources. And it's less restrictive than the XML type since it doesn't follow markup rules. And so you can actually retain the same data at a less size, simply because you cut down the verbiage of XML. You don't have to have that open closing of the same names. You can just follow the square bracket and the curly brace format. And so this is how the analogous version of the XML looks into the JSON format. And this is a very flat file. Again, the easiest to work with. JSON, much like XML, can extend into more complex nested formats. And so here, collections are denoted with the square bracket. And so we have a collection here, and then within the curly braces, that key value pairing. Where essentially each of these keys will map as columns, and then those corresponding values will become values within the columns, and then it extend, and then each of the collection becomes delineated by rows. In R, you want to use the JSON Lite package. Include that into your core because it's a very powerful, lightweight package to really navigate through JSON. Great feature. If you have a very flat JSON as shown here, you can map them easily straight from its text file directly into the final format. And then you can actually even, if the JSON is in a string format that you probably pull from a web application, you can map that easily with the same method, and so get a nice tidy data set overall. Now, as said, JSON can extend into more nuanced ways, and much like the XML nested example, we can now encapsulate certain key value pairs within its own encapsulation. So all the station data will reside in the station element, and all the rides within the rides element. So we now have to navigate into a denser, a second level nesting to extract the data into the flatter 2x2 dimension of the row by column data frame structure. So with that, what you want to do when you get such a very complex JSON, you first want to set up a staging object. And so here we essentially assign to a raw object straight from that nested file type. And as you can see, when we run our structure call, we have a very dense setup. We have a data frame. So this is essentially a list of objects. The first list is a data frame, and then we have a vector, and then we have another data frame. Fortunately, these are all the same levels: 10 observations, 10 vector values, and then 10 observations for this rise data frame. And so we just need to really bind all those specific elements together to flatten it out into a nice data frame format. Of course, this can get a lot more complex. This is a very easy to use. You may have to call several sapply, lapply calls, various iteration loops to map those values into this data frame caller or cbind or even R bind structure. And so again, you want to use that staging object to really be the catapult to bind all your needed data elements together. So overall, I hope I was able to really give you a broad stroke of how to really work with nested structures in R. These are formidable data types. Again, it's expressed in a very different way than the more popular text delimited formats, and so it requires the data analyst to really work with various tools to navigate through. So again, thank you for your attention and your time, and I hope this was helpful.